We defined in the previous lecture an intuitive concept of an automaton, and in this lecture we are going to give the formal mathematical definition of what an automaton is. And in this lecture we in fact focus on the deterministic form, so deterministic finite automata. Deterministic automaton, deterministic finite automaton is a construct like this. It has several components. I'm writing them down and then I explain what each one of them is. It's made of a Q, sigma, delta, Q0, and F. And the meaning of all of these components is the following. Q is a finite set of so-called states. And the fact that this is a finite set gives you the word finite in deterministic finite automaton. And then you have sigma. This is the input alphabet, meaning that this automaton will have in its input words over alphabet sigma. Delta is a function from Q times sigma to Q, and this is called the transition function. And I comment on this in just a moment. We have the Q0. It's one of the states in Q, and this is called the initial state. And also I comment on this in a moment, what's the meaning of initial here. And then F is a subset of states, so F is included in Q, and this is the set of final states. So you might have several of them, all of them are collected in set F. So you have a set of states, a finite set of states, you have an input alphabet, you have a transition function, you have the initial state, and you have a set of final states. So this is what an automaton is. And I also, before I go any further, I also make the point that we can in fact indicate this visually, similarly like I did in my previous example. We can indicate, so describing a visual representation of an automaton. You could visually represent this simply in the following way, as a graph, where the nodes, they are all the elements of Q, and you have edges from P to Q whenever delta of P, you will also have a labeled, so you will have a label on these edges whenever from a delta of P and A is Q. So these edges, they are for PQ in Q, and for a letter from alphabet sigma. So what this looks like is, I'm going to have, just like we had in the example in the previous lecture, we will have nodes in this graph, one node for each state, and we will have edges, and these edges will be in fact labeled edges, and they will have the label of that character that indicates how from delta you go from P to Q. So from delta, with delta you go from P to Q through letter A, so you have this condition, delta of PA is equal to Q. And another way to represent this, so alternative visual representation. This is going to be useful when we show computations in this automaton, but I come back to this point. Alternative visual representations Simply, you can just write the sequence of states. So you could say, in this case, when you have delta of P and A equal to Q, you could say that once you are in P, you simply go to Q and you indicate the letter A, and you might have several such transitions with other letters. So this simplifies. It's the same idea of having a graph, but it simplifies. You don't highlight necessarily so much that these are nodes. It's just a sequence of states, and you show in between states what was the letter that transitioned from state P to state Q. So the idea of this automaton is that you will have computations, and these computations are nothing else than just transitions from state to state and driven by your transition function. So any such computation in the automaton A will start from the initial state, and it will be driven by an input word. That input word is going to change the state letter by letter. So to formalize this, I'm going to extend. So I will extend this transition function. Right now, the transition function in the basic definition is just defined on how you change from one state to another state while you are reading one letter from the input. I'm going to extend the transition function to reason about how we can advance our computation with more than one letter, maybe with full words at a time. So I'm going to extend this to a function that I also denote by delta. I'm abusing a little bit in notation here, but hopefully this is not going to be too confusing for you. So my extended definition of delta is going to be a function that maps a string and a word, not just a letter like before, but a word, to another state. And the idea of this transition function is that when you are in state Q and you read from the input this particular word, the result is going to be a change of state, and as described here in the result. And the way this is defined based on the basic definition of delta is going to be in the following way. So delta of Q. Now, if you read the empty word, then there is no change of state. So you are going to stay in Q for any Q in your set of states. And if you have, from Q, you read something where there is at least one letter, then you will have a computation where you first go from Q with word W to whatever state your delta is bringing you, and then you do one more step in your computation driven by letter A. So the idea is that you do this computation step by step, first driven by this prefix, and then one more step driven by letter A. So once we have this extended definition of the transition function, we can now define what does it mean to have a computation in an automaton. So we will say that I'm going to continue on the next whiteboard. So remember that the initial state is Q0. And the reason we call this initial is that any computation starts in Q0. So if I have an input word W on sigma star, then we are going to have a computation starting from Q0 and driven by W. And so the computation on input W starts from the initial state and ends in this state where delta is going to bring you. So the result of this function, delta of Q0 and W. And the point is this, that we are going to have computations of two different types. So the computations the computation on W can be either accepting, so we will say this is an accepting computation, or it can be a rejecting computation. And this is an accepting computation if delta of Q0 and W, if this happens to be a final state. So it's an accepting computation if when you start computing from the initial state and you go letter by letter through your input, at the end of the computation you end up in a final state. And it's going to be a rejecting computation if delta of Q0 and W is in any other state but F. It's in a non-final state. And so in this case, this is the keyword here, accepting and rejecting. In this case, we also say that W is accepted. So accepted by the automaton A. And obviously in this case, we say that W is rejected by the automaton A. And we also have, we also say that W is recognized. This is also a keyword, is recognized by the automaton A. And here we don't have a special word, we just say W is not recognized. By A. So here you have it, you have the idea of a computation on an input word, and the way the computation goes is really driven by the definition of delta. You start in Q0 and you read the first letter of W, and that takes you, so if W, for example, is A1, A2, all the way to AM, with AI being letters of your alphabet, then your computation will start from Q0, and you read letter A1, and that's going to bring you to a state Q1. This Q1 could be Q0, depending on what your delta function is, but it could also be a different state. And then you read the next letter, and that's going to bring you to another state, Q2, and so on. In the end, you read the last letter, AM, and that takes you to a state QM. And the idea is that you have done a computation. You went from state Q0 to state QM, and then you are checking if this QM is a final state. Then you will say that this is an accepting computation, and you say that W is accepted by the automaton, or that it's recognized by the automaton. But on the contrary, if QM is not a final state, is not in F, then you will say that W is rejected by A, and that W is not recognized by A. So you can think about this automaton as doing, if you like, calculations or computations on the word W, and at the end giving you an answer yes or no, and accepting or rejecting, or recognizing or not recognizing your input word. And so with this in place, now I can define the language. So the language accepted by the automaton A, and we also say accepted or recognized. Denoted the language of A. So the language of A is simply the set of all possible input words, so all W in sigma star, with the property that really from Q0, doing a computation on word W takes you to a final state. So it's a set of all W such that delta of Q0 and W is a final state. So I promise that I will come back to this idea. What does it mean that we are dealing with deterministic finite automata. So the word finite, I already explained. It has to do with the fact that your set of states is finite, and you can think about your set of states as being the only memory you have in your device, in your automaton. So having just a finite number of states, it means you have finite memories, hence a finite device. But the word deterministic is really more subtle. It has to do with the fact that really your whole computation is driven by a function, and this function by default, just because it's a function, it means that when you are in a state P and you read from the input a certain letter A, there is only one possible transition, and that's exactly the transition specified by your function delta. So in other words, when you are in this state P and you do a computation with letter A, this computation is deterministic. There is only one single possible output to this computation. From P with letter A, there is no other way than to go to Q, which is exactly what delta is saying. And it might be somehow obvious to you that it should be like that. But in the next lecture, in fact, I will discuss a different form of automata where this computation doesn't have to be deterministic. You will have, for each step, potentially several options for how to conduct your computation. But for now, we focus on the more elementary version of automata, and that is this deterministic automata. So again, deterministic, it means that every single step of your computation is uniquely determined by delta. Your computation is deterministic. I want to give you an example to see how all of these things look like when we take a less abstract view on what automata are. So let me take an example. And for example, I could take this example of an automata which is given by a set of states made of 4 states, and I'm going to just denote them by 0, 1, 2, and 3. And it has an input alphabet made of 2 letters, A and B. And it has a transition function that I'm going to define in a moment. 0 will be your initial state, and 3 is the only final state you have. And I can show this delta through a table, so through a transition table. So I can say that delta, so remember that delta is defined on Q, which in our case is 0, 1, 2, 3. Times sigma, which in our case is AB, and it takes values in a state of states, so 0, 1, 2, 3. And I can define this, obviously, delta by having a table, so that's our delta, and 0, 1, 2, 3, these are all the states I can possibly have, and these are the input letters I can have. On this transition table, very often we also indicate, just for the sake of completeness, we also indicate with an incoming arrow that this is your initial state, and we can indicate with an outgoing arrow the fact that this is a final state, just like we have here in the definition. And so I can define in this example to have delta of state 0 and letter A to be set state 1. And I can define delta of 1 and A to be 1, delta of 2 and A to be 3, and delta of 3 and A to be 3. And delta of 0b, I define it to be 0. Delta of 1b, I define it to be 2. Delta of 2b, I define it to be 0. And delta of 3b, I define it to be 3. The same thing, I can also, so this is the transition table, and I can also define the same thing through the graph I mentioned on the previous whiteboard. So this is going to be the transition graph. or if you like, the directed graph view of the automaton. So for this graph, I'm going to have 4 nodes, one for each one of these states. So I'm going to have 0, 1, 2, and 3. And I indicate that state 0 is your initial state by having an incoming arrow. And I indicate that 3 is a final state by having an outgoing arrow. In some textbooks, the outgoing arrow is skipped, and instead they indicate that this is a final state by having a double circle on 3. So either one of them, or both if you like, but either one of them is enough. And now we consider state 0, and we are reading from the table. So from 0, with letter A, you go to state 1. So that means that I'm going to have an edge from 0 to 1, and I put label A. And that means that delta of 0 and A is 1. So from state 0, I go to state 1 whenever I read an A from the input word. And delta with 0 and B is 0, so I have a self edge here on 0, and the label is going to be B. So from state 0, with letter B, I go to state 0. And then from state 1, with letter A, I stay in 1. So I'm going to have a self loop here with letter A. But the transition function is saying from state 1, you go to state 2 if you read B. So I have this edge here with label B. And from 2, I go to state 3 with letter A. And from 2, I go to state 0 with letter B. So I have this part. And finally, from state 3, with either A and B, I stay on state 3. So this is denoted in this way. I could have a second self loop, but I can also indicate just on this self loop 2 different labels, meaning that really from state 3 with either A or B, I stay in state 3. So this is the graph view of the same automaton. So we can check a few computations in this automaton. So for example, if I have input word say B, A, B, A. And so we can calculate. I'm going to do this, as in the definition. So doing a computation, it means that you start with your delta from the initial state 0, and with this word as your input word. And this was I'm just going to write, and then I'm going to comment. There is maybe a place for a comment here. So I would like to show this calculation like this. And the comment I want to make is that on the previous whiteboard, I had defined it, on words in a different way. I said that first you do this whole computation on these words, and then you apply one more computation on this word. Whereas in fact in here I'm showing that first I do a computation on this letter, and then from the next state I do a computation on the remaining of this word. It turns out that it doesn't make any difference for how automata work if I explain it one way or the other way, but there is a little bit of difference between how I had the definition on the previous whiteboard and how I'm driving the example here. So I'm sorry about that, but there is no mistake in here. So let's focus on this. This is also easier to follow if I do letter by letter from left to right. So again, doing a computation from 0 with this big word BAA, BAA, this is the same as doing a single step with letter B, and that will take me to a new state. And then from that new state, I continue with my computation on the remaining word. So delta of 0 and B, that's 0 from the transition table. So that's going to be delta of 0 and the remaining of this word, A, A, B, A, A. And in the same way, this is going to be, I do now computation from this state with the next letter, A. And then the result will have to take me further with the remaining of the words. So A, B, A, A. And again, I check delta of 0 and A. That's 1. So now I have to do a computation starting from state 1 with this word A, B, A, A. And that's the same as doing one single step from 1 with letter A. That's the first one here. And then from whichever state I land in, I do a computation on the remaining of this word. And delta of 1A is 1, so that's going to be a delta of 1 and BAA. And it continues in the same way. Now I can speed up a little bit, and it's going to be 1 and B is going to take me to state 2. So I'm going to be in state 2, and I have to do a computation on the remaining letters, AA. And then in state 2, I go with A, which is the next letter here. I'm going to go to state 3. So then I'm in state 3, and I still have to handle one letter from the input. And finally, 3 and A, the transition function says that you are going to be in state 3. And then I'm checking whether state 3 is final or not. And this is, in fact, in our example, a final state. What this is, we conclude that this is an accepting computation. Meaning that the word that we had in the input, meaning BAA, BAA, is in the language of A. So it's accepted by the automaton, or we also say that it's recognized by this automaton. Here is another computation. If I am to calculate, from 0, so I do a computation on, so I write here, input this time is going to be the word ABB. And so to consider this input, I will have to do again a computation starting from the initial state 0 with this input word ABB. And that's going to be like this. It's going to be, first I do a step from 0 with A, and that will bring me to state 1. So I will be in state 1, and I have to handle the remaining of this input, so BB. And then from 1 with letter B, I go to state 2. So that will bring me to state 2, and I have to handle the remaining part of the input. And from 2 with letter B, I go to state 0. And 0 is not in your final set of states, because the final set of states was made of just letter 3. So this is an rejecting computation. So we say that the input word we had is not in the language of A. We also say that it's rejected by the automaton, and we also say that it's not recognized by the automaton A. And we don't really have the tools to handle this, but we will get them next week. In fact, we can establish, we can calculate, and you will be able to do that by the end of next week. The language of this particular automaton can be described as being exactly this. It's AB star, A, B, A, AB star. So I don't insist on this. My only point is that I want to announce that you will get the tools to really calculate exactly what's the language of a given automaton.